Hey dudes, Dude the Builder here. In this episode of Zig Master, we're going to be talking about slices in Zig. And we're going to be doing this in a more bottom-up fashion. We're going to be trying to explain why we need slices, and from there we can see exactly how we work with them in Zig. So to start out, let's make a little function here called display. We have an items parameter. And let's say that this parameter is an array of 3 bytes. Okay. And then what we're going to do inside this function body, we're going to loop. We haven't talked about loops, and we will in the series, but for the purpose of the example, it's pretty simple. We just loop from 0 to items.len. Okay. And we're going to capture that index, and we are going to print item and the item index, and then we need the actual item value, and here the index and items and the value. Okay, so we have that little function, simple. Here, let's create an array equals. Let's use the literal syntax 0, 1, 2, and then we call our function with the array. Okay, so easy enough. We have our little function to print out the items of an array, and let's compile and run this. And it works. Okay, we are displaying here, printing out each of the items on a separate line. So that's working. But this function of ours isn't really flexible, because if we have an array that instead of 3 items, now we have 5, we try to run this, it doesn't even compile. Okay, so we're going to get an error here stating that we are expecting an array of 3 bytes, but we got an array of 5 bytes. Okay, so we have a situation here where when we call this function, and this is an important detail, when we call our function, we are in runtime. Okay, so at runtime, we would need a way to handle sequences of different sizes, not just a fixed size array as we're doing right now. So one way to handle this is the way that it's been handled in C for a long time. And what we can do here is, instead of items being the fixed size array, and with the tools that we have up till now, we know that we can use here, for example, a many item pointer, and in this case we're not going to be needing to mutate, so it'll be a many item pointer of const u8, and we can pass in a length. Let's make this a U size. Okay, and now what we would do is, here we would go from 0 to len, and then instead of indexing an array, we are actually using that multi-item pointer here with the handy indexing syntax, which basically will behave as if we were indexing the array itself. Okay, so now we have to modify here. We can take the address of the array, which will coerce to that multi-item pointer. Okay, and here we pass in array.len. Okay, now let's see if this works, and it does. Okay, and let's, for example, if we delete here these items, we change the length of that array, and we run this, it still works. So with that, now we have a version that can handle different sequence sizes, okay? And when you have a function that has these parameters that are related, okay, here items is a sequence, and length here is that the length of that sequence. So these two parameters are basically describing a single entity, which is that sequence of items in memory. So the next logical step would be to create a data structure. For example, let's say here const slice equals struct. And we haven't discussed structs, but also for the purpose of the example, it's going to be pretty intuitive. We have the pointer, which is going to be a many item pointer of const u8. And we have the length, which is going to be a u size. So now we can change here and say that this is going to be a slice. Okay. And now we go back here to saying items.len. And over here, it would be items.pdr. Okay. Now, here in the actual function call, we can use the anonymous struct literal here. We say that the pointer is equal to this. And here we say that the len, .len equals that. We insert the closing curly bracket. And now, let's see if this compiles and runs. And it does, okay? So basically now what we have is that we created this data structure that encapsulates this notion that we're going to have a sequence, and we have this many item pointer to that sequence, and we have the length of the sequence, and we can just pass that into our function. And you can probably know where I'm going with this. This is exactly what Zig provides built in with its slice type. So here items can be represented by the slice of const u8. The slice type is the square brackets without anything inside, okay? In contrast to the array that has the size as part of the type. In the case of the slice, we have nothing, meaning that the length is going to be determined at runtime, okay? So now we can change this back here. We don't need this. We can just use the indexing syntax directly on the slice. And we do have a len field, as we do with arrays. And now here we can just change this to being taking the address of the array. Okay? So let's compile this and run this. And there we go. It works. Let's change this length here, and it still works. Okay, so with that, you can see why the reasoning why we need slices. It really comes in handy when you want to be flexible, defining a function or any type of API that requires handling of different sizes of elements in memory. Well, the slice will encapsulate that notion in a data structure that, as you have seen, it has a pointer and a length. Let's see here an example. Let's create a slice explicitly. Let's say slice here. It's going to be a slice of const u8. And once again, we take the address of array. Okay. And now in here, we can just use that slice. Let's test this. Okay, it works. Now, here we're taking the address of the array, which will actually produce a pointer to an array, as we've seen previously. And that pointer to an array can be coerced here. We're explicitly specifying the type to be a slice of const u8, so it'll be coerced to that slice type. Another thing that can be done is using what's known as slicing syntax, okay? So let's say that here I want the first 2 elements, okay? This syntax here with the 2 dots, this is what's known as slicing syntax. The 0 and the 2 are what are known as the bounds of the slice syntax. And here we're basically saying that we want to start at index 0, and we are going to include in this slice up to, but not including, index 2, okay? So what this basically does is it includes 0, which is at index 0. It includes 1, which is at index 1, but it does not include 2, 3, or 4, okay? And one little benefit of doing slicing like this as 0 indexing is that if you subtract the end bound, you do a 2 minus 0, it tells you how many items you are actually slicing. So here 2 minus 0 is 2, so you are slicing 2. This will be a slice that has 2 elements, okay? So if let's save this and run this, and there you go, you have those 2 elements, okay? Now what happens if we don't specify here the type? Okay, so we're just declaring this slice constant, and we're slicing here the array. Let's run this. It works, okay? Now let's see explicitly. This is type of slice, and let's use the type of built-in and slice here. Let's run this, and it says that the type of the slice is a pointer to a constant array of 2 bytes. So this can be a stumbling point for newcomers to the language, because once again, we saw an example already where with string literals, a string literal is actually a pointer to an array, because a string literal, everything is known at compile time, so we don't need any runtime knowledge here. So a slice, the length, one of the features of the slice is that you can know the length at runtime versus the array where the length has to be known at compile time. But here we are specifying that we start at 0, we go up to 2, so we know the length is known also at compile time. So when you have a slicing syntax and you're using bounds that are known at compile time, you are going to obtain a pointer to an array. Once again, an array is going to be created by the compiler, and you will receive a pointer to that. And in many circumstances, as you saw here, everything works because that pointer to an array can be coerced to a slice, okay? Now, if we can demonstrate, let's create here a variable called start. Let's make it a usize. Let's say that we want to start at 2. And here it's telling us that it's unused. So let's use it here. Let's say start. Now it's telling us that the variable is never mutated, and we can fix that error for the sake of the example by taking the address of start, okay? And now let's save this and run this again. And now you see that the type of the slice is indeed a slice of const_8, okay? And we don't have any output from our display function because the start and the ending are equal, so this slice has no elements, okay? But the important thing is that now, since we have a runtime variables have to be runtime, even though here we're specifying an initial value which is comp time known. Since here, for example, we take the address of start, this is the type of situation that the compiler cannot assume that start isn't going to change later on in the program. And it could change to a runtime only value. For example, some input from the user or something like that. Or something that you read from a file or receive from the network. So variables are inherently runtime only. And that's why we're forcing here this slice to be an actual slice instead of a pointer to an array, because we have one of the bounds is actually only runtime known. Okay. Now, you could have also the situation, let's copy this, which is pretty common. Let's change this to len. Let's say here that we want 3 items, and let's also change this to len. And now we have here len, and if we save this and run it, you're going to see that once again we have a slice, but this time we're only printing out one item, and it's item 2, the value 2. Okay, but what happened? We actually wanted the length. Well, if you're starting out from 0, let's make start here 0. Let's run this again. Then you'll get what you expect. Okay, when you start out from 0, you can use a length as the ending bound, and there would be no problem, because basically the length and the index of the final element, the one that's one past the last element that's going to be included, it's going to be the same thing. But when the start bound isn't 0, then the length is not going to be equal to the index. Okay, so basically what this tells us is that this final ending index isn't the length, isn't how many items you want. It's actually the index that's one past the final item that's going to be included. Okay, so in here, to obtain the actual result that you want, you would have to do a start plus len. Okay, now if we run this, we obtain the actual 3 items that we wanted. Okay, but this is not the recommended idiomatic way to do this. There's a better way to do this, and let's demonstrate it here. What you would do is you would first slice from the starting bound that you want, and then you would do a reslice, okay, from 0 to len. So basically here I'm saying I want a slice starting from here, and from that slice I'm going to reslice from 0 to len. Okay, and behind the scenes, let's save this and run it, and there you go, you get the expected output. Behind the scenes, the compiler will optimize this to a single operation. So this is why this is the recommended syntax. It reduces the possibility. It's less error prone, because now you don't have to be doing that calculation of adding the length to the starting point. You just slice from your starting point and then reslice from 0 to the length. Okay, so this is the idiomatic way to do this. Another thing I wanted to mention is that you will also see, if we specify here explicitly, for example, here, that this is going to be a slice of const_u8. So let's name this slice over here. Let's eliminate this. And now you will see sometimes this type of syntax. Let's change this. And dot. Okay, so let's run this, and there you go, it works. This is basically 2 steps here, the dot curly and the list. This is what's known as an anonymous struct literal. It could also be a tuple, but in this context we're specifying that the result type is a slice of const_u8. So this will be basically coerced into an array, because we can define an array using this dot curly brace syntax. And then the ampersand is taking the address of that array. Okay, so behind the scenes, the array is going to be created, it's going to be allocated, it's going to be put in the static block area of memory. then we're taking the address of that, which will create a pointer to an array, and then that's coerced to a slice of const_8. So whenever you see this syntax used, that's basically what's going on. Now let's return this to how it was. Okay. And one other thing I wanted to mention is that we can have also what's known as a Sentinel-terminated slice, just like we saw with Sentinel-terminated arrays and Sentinel-terminated pointers, the multi-item pointer. So let's create here const. Well, actually, what we can do is let's go up here to our array. Let's add here a 0. And now we can say that we want a const s slice. It's going to be a Sentinel-terminated slice of const_8. And how do we create this? Well, we are going to use the slicing syntax once again. Let's say here array 0 to array.len -1, and we add a :0. Okay, so this is the syntax that's used when we want to slice with a sentinel. So basically what we're saying here is we have the array length, but we're saying that our slice is basically going to be one less the length of this array, because the final item here is going to be the actual sentinel. Okay, and now let's repeat what we have here. Let's copy this and let's insert here and that, and here let's do the same thing. Save this and let's try to run it, and it works. Okay, so now for slice, it's telling us that it's indeed a Sentinel-terminated slice of const_8, and we go from 0 to 4. Okay, and once again, these types of slices may come in handy when we're dealing with, for example, C code, that in the case of C, the null-terminated strings, it's one situation where they can come in handy. And here, let's also see one of the, we can say that slice, whoops, and here slice, whoops, slice.len. Let's run this. And as you can see, slice.len is indeed 0, that sentinel value. Okay, and that's something that if, for example, we try to do this with a normal slice, with our previous slice, we try to build this and run it, we are going to get a runtime panic. Okay, so as you can see here, we have a panic. It says index out of bounds, index 3, length 3. And this is another feature that you're going to be getting used to in Zig. There's a difference. When we had a compile error, it said error, and it marks it as red in the terminal. When we have a runtime panic, it's going to state it like this, a panic, and the type of error message. So the difference is that a compile time error happens at compile time. The program is not running yet. And a panic happens at runtime. So the program did compile, but there's a problem generated while the program is running. So basically, this demonstrates that in a normal slice, you can't access the item at the length because there should be no item there. But in a Sentinel-terminated slice, the item at the length is the actual sentinel itself. Okay, and with that, that's basically what I wanted to demonstrate about slices in Zig. That you're going to see them used extensively because they're really flexible. and a really powerful feature in the language. You have to be aware of situations like this one where you have comp time only bounds. You're going to receive actually a pointer to an array, even if you are using the slicing syntax. But aside from that, if you're aware of those details, it's a really powerful tool in your tool belt. Okay, so I hope you find this useful. Do the builder here. I'll see you in the next one.